quick gander, make sure you got your highlights. Good. Flip for me, flip for me. Okay, I'm going to do you one right now so you can finish off what you. Sure, want to take your center, right? Yeah, got one more. Go ahead and hold questions. Not to do two sets. Go ahead. Good. 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 Awesome. Awesome. Let me see 2-1. See me today, right? Okay. Catch some of it up while you're all going. Right. Catch. All right. Let's quickly look at some of the things that you highlighted. Just want to quickly see what you got out of your reading from last night. I want to go with yellow. Okay, so quickly, first things you highlighted right there. Yes, Aiden.
Any layer equation can be written in the form y equals mx plus b, where m is the slope and b is the y-intercept.
Okay, did you do it right here in this top one or down a little further?
It's further in the slope-intercept form.
All the way down. Okay, I'm going to come back to that, Aiden. Let's start at the top and work our way down. You know how we do sometimes for the homework problem, instead of us flipping all over the place. Let's start at the top. Okay, what was the first things that you did? How many people highlighted all three of these bulleted points? Excellent. Most definitely should have. Most definitely should have. In the last section, we talked about linear functions being graph of a straight line, being in the form y equals mx plus b, where m is the slope and b is the y-intercept, and the function having a constant rate of change. There was something else that we talked about that I think is very important that's not listed there. So I want to add it. Can anybody tell me what it is? What's the one thing that we talked about that's not there? Nick?
The x, the x doesn't have an exponent.
Very good. Everything's to the power of 1. So let's add that in there right now. Let's put another bullet and say, hey, a linear function or a function whose degree, well, I can't spell today, sorry, whose degree is 1. Function whose degree is 1. Remember, we talked about it being linear functions being functions to the first degree, or as Nick started to say, doesn't have an exponent, right? I mean, it has it. We know it's there, but we don't talk about it. That was really cool. I just highlighted that. I wrote it in red ink. A lot of times I do that on paper. I write it in red ink, and then I highlight it, and it smears all the ink. Didn't do it this time. Isn't that cool?
No red ink.
Thank you, Gia. Somebody got it. It's on a computer, duh. Okay. Next paragraph. Next paragraph. Or next section. Input and output. Independent variable and output. Or dependent variable. Okay. Something you highlighted in that section. Quickly. I don't want to spend much time on this reading. You read it. You highlighted it. Shelby? A function is a rule that assigns each input exactly one output. Okay, I like that. A function is a rule, assigns each input exactly one output. I like that. And the second sentence, it is crucial to understand and identify the input and output or multiple forms of a function. Okay. Let's slide on down. Now, before I go any further, look at those 3 examples right there. This is what we're going to spend a lot of time talking about as we contextualize. What does contextualize mean? That's a big word, lots of syllables. What's contextualize mean? What's the root word? Context. What does context mean? put it into different words or into a situation, right? So we're contextualizing here. We're going to look at the real world situation. This is one of my favorite sections because this is where we take the math and we realize that math isn't just numbers. It's logic. It's problem solving. Okay, now we're going to look at 3 different situations throughout this whole section. We're going to look if we're given an equation. Man, that's really easy to see. I think you'll agree with that. And then sometimes we'll be given a graph, and sometimes we'll be given a situation. We got to be able to find or decipher what's going on and what these important parts are in each of those. So let's jump down here a little bit. What is the input or the independent variable? That's highlighted or it's bold, so you should have saw that really easy. What is the independent variable? It's the input. It says it right there. The next paragraph. What's the dependent variable? It is G here, but what is it? It's the output, right? The output is also known as the dependent variable. Down here, I want this one. I'm going to put this in pink, and I want to explain this. In the standard equation form of a linear function, y equals mx plus b. I have a little problem with this. It's just a minor problem, and I want to explain it to you because it allows me to explain something else to you. I don't like the fact that they called this standard equation form of a linear function. Y equals mx plus b. We've already named that, haven't we? What is it called? What do we call it? Slope-intercept form. So for right now, I want you to please cross out standard equation, and right above it, I want you to write slope-intercept. I want you to write slope-intercept. And then I'm going to take a little time out here, and I'm going to explain what I'm talking about. See, this thing happened to call it standard form, and it's not totally wrong because later we're going to talk about polynomials, and we're going to have big, long functions like this. For bonus, for 1,000,000 bonus points, who can tell me what kind of function this is, the name of this function? 1,000,000 bonus points that don't count for anything. Moss? It isn't standard form, but I don't want to know standard form. I want to know what the name of that function is. I'm going to give you a hint. Dog squatting.
Oh, they're Indian boy.
Indian boys. How are the Indian boys named?
Whenever they came out of the tent.
First thing they saw, right?
We named them.
Okay. How do we name functions? Yes? By their degree. What's the degree of this function? So what's that called? Something to the 4th degree. And if you say quadratic, I'm going to smack you in the back of the head. It's not quadratic because quadratic is 2, remember? Because of the nickname squared. It's not quadratic, it was quantitative, no. I like it though, he's thinking.
Wait, Quint is 5, right?
Quint is 5.
Quarters.
Yeah.
Quartic, as a quartic function. Okay, so back to it. This is what we'll have things that'll look like this. And we consider this standard form when we talk about polynomials because we have our terms lined up from high to low. In other words, the exponents, from the highest exponents to the lowest exponents. That's considered standard form when we get to polynomials and stuff. So in one essence, y equals mx plus b, or let's give another one. Y equals 2x plus 1. That is a polynomial too, the 2x plus 1. And it kind of is in standard form because our degrees are lined up from high to low. I get it. And that's why this text said that. But I don't like them calling it standard form here because linear equations have their own standard form. You need to write this down. It's not in your reading at all from last night, okay? Linear equations have standard form, and it looks like this. I'm going to go with red so it jumps off the page at you, okay? Standard form or linear standard form looks like this. Ax plus by equals c. Ax plus by equals c. And then I've got 2 little bullet points here that are important. The first one is A, B, and C must be integers. Well, I'm screwed now, Coach Herman. I don't know what integers are. You can tell me what integers are. Ashley? Good. They're all the positive and negative whole numbers. So think about that. Integers is just a cool word that says positive and negative whole numbers. No fractions, no decimals. Good. We don't like fractions and decimals, right? So we should like integers. Not integers, but integers. Okay. So A, B, and C got to be integers. So there's not going to be any fractions or decimals in there. The other thing that has to be true is A must be positive. Now, I'm giving you that information right now. Boom, linear standard form is AX plus BY equals C. You're writing it down. We're not going to spend any time on it right now. It's just foreshadowing for the future. We'll talk about that down the road somewhere, okay? I just wanted to clarify it for you, all right? And one more time, Y equals MX plus B. What do we call that?
Slope intercept.
Very good. Slope, intercept, form. So let's look at slope-intercept form a little bit closer because I think it talks about the linear function that we're dealing with. Again, one time, what is a linear function? There's like 4 definitions. What is a linear function? Josh? Any of the ways you know something is a linear function? Okay, that'll tell us it's a function. I need linear function. Ezra? Very good. Must be to first degree. I like it. That's one. Another one. Yes, sir, Zach. Awesome. Constant rate of change. I'm just going to leave that as the rock, right? Constant rate of change, a rock. One more. Yes. Straight line. Graph is a straight line. Sorry about my lag. All right, so it's Y equals MX plus B. There's my M. There it comes. It's lagging. All right, so what is this first Y? It's another name for the Y. Yes, sir. Okay, I'm going to put that over here to the side. F of X equals Y. You're absolutely right. That's something we learned about function notation. Good. What else? Another name for the Y. Yeah, it's the output. Output. What's another name for the M? Oh, go ahead. You had something else. Go give it to me. Whatever you say. The range. The Y is the range. Excellent. Oops. I need to go to my other color. You got me going. There we go. All right. Another name for anything up there. Yes. M is the slope. M is the slope. Good. Yes, sir? B is the initial value. You know what? I'm going to put that down here. Perfect. Initial value. All right. Another one. Yes, ma'am. B is the y-intercept. Excellent. Y-intercept. Keep them going. We got a lot more. Yes. X is my input. Good. Give me another one for slope. Give me another one for slope. Yes. Ooh, I like it. Rise. Overrun. Give me another one for my input or my X value. Yes. Domain. I think we could do one more for each of them. Somebody give me another name for your output or your range. And I'll give you another hint. You just read about it. Yes. No, we already talked about that one. Yes. Yes. Dependent variable. Very good. Dependent variable. That's kind of one of the major focuses of your reading last night, right? Is it be calling it a dependent variable? Because when we talk about it being in context, this variable, the output, depends on what the input or the independent variable is. All right, so what's another name for slope or rise over run? Rate of change. The rock, the rate of change. Good. Another for input. Very good. Independent variable. And last one, I need one more. Don't be stumped. Yes. Constant. Constant. Think about all of that stuff that we've learned already this year. This is where confusion happens. We've got all these different names for the same stuff. Absolutely, it can be difficult, right? Savannah? Savannah Benson? Miss Benson? What's your middle name?
Hope.
Hope. Savannah Hope Benson. All those different names for the same young lady, right? Same thing here. We have all these different names. It's not a big deal. Can you handle it? Remember, just like in the last section, sometimes I would take the name like domain. We still struggle with domain sometimes, right? But if we just cross that out and say the input, it makes our questions a little bit easier to deal with. Can I get an amen?
Amen.
Amen. All right, let's go back to your reading. I want to see if there's anything else that we needed to jump on here. Kind of got sidetracked about talking about, I wanted that to be used slope-intercept form. How about rate of change? Something in there that was important to you in rate of change. Don't everybody talk at once now. You already have it highlighted. Nelson, what you got highlighted in there? In that whole section for rate of change? Okay. Anybody else? Nobody? Nothing for that rate of change? We just know that rate of change so well. Shelby?
I basically highlighted like mostly everything because I thought everything was important for that. So,
All right, so in example 1, the rate of change is given in the equation as slope. Y equals mx b. Note that 100, which means the rate of change is also 100 or 100 over 1. This means that grapes grow for 100 grapes grow for every one branch. You didn't like highlighting all that?
no, I don't know how to make an example because only pertains to the one problem.
I'm okay with that. Is it okay that Shelby maybe highlights all of it and Ashley doesn't?
Yeah.
Yeah, because it's what makes sense to you. Maybe the example is exactly what Shelby needs, but for you, you just want to know that definition. Like I just did like input, and independent variable, and that's perfectly fine. That's what it's about. That's why we read and highlight, right? It's what makes sense to you, what helps you remember. So, and that's why I don't make a big deal about, hey, this is what you need to have highlight, because it's what helps you. All right, let's move on to initial value. Something that jumps out of you at initial value. It's like for me, the initial value is the y-intercept. I mean, that makes sense to me, okay? And so on, okay? So, all right, enough of that. So here we go. Let's look at it in context. How many different parts do we have of this equation? One more time, what is the equation? And everybody said? Ooh, I thought I said everybody said, not just Gia and Zoe. Let's try it one more time. And what's the equation? And everybody said? Let's try it one more time. And everybody said?
Y equals mx plus b.
How many parts are there? 4. We got our output, our rate of change, our input, and our initial value. Okay? If you can figure out what those 4 things are, then we can look at the context of the situation and say, This is what this is. This is what that is. And then we can come up with the equation of the line. Okay, we're going to be looking at it in 3 ways. We're going to have an equation, we're going to have a graph, we're going to have a situation. Can we find those 4 parts in each one of them? And then figure out what they're talking about. I like the context. So let's look at question number 1. We need to identify those 4 parts and then describe them in the situation. Okay, so a 2.5-foot rocket's distance traveled in meters, d, based on the time in seconds, is modeled by the following function. First, what is the dependent variable, and how do you know? Aiden, how do you know? Ooh, that's terrible. What's that? Oh, you don't know, you just got a brain? Is that what you just said? How do you know it's D? Just a lucky guess?
No, I know. I can't put it into words.
Okay. Well, that's what context is about. We want to take what you know and be able to put it into words. Moss?
It's D because D equals 5T.
So you say it's D because
Y.
the D is by itself.
Yeah.
It is the Y. Okay. I'll give you that. Ezra?
Because since D equals that step, D can't exist without the other.
Ooh. D can't exist without the other. I like it.
It's dependent.
But you again knew by looking at the equation. Is that how you determined that it was dependent? Okay. Both of you perfectly good. Nick?
Because it's where the dependent variable would be in slope intercept.
Okay. Again, he's looking at the equation and noticing that that's where the dependent variable would be. I mean, the D is in place of the Y here, and that would be our dependent. Gia, did you have a different reason? Anybody have a different reason? Okay, there's absolutely nothing. Those are all perfectly fine. What if, though, I didn't have that equation? Can we look at that situation and determine which one is the dependent without the equation? Gia?
Well, in the first sentence it says it's based on the time.
There you go. It's based on. This D is based on the time. So this one needs the time, right, to exist, as Ezra said. So it's based on. So I want you to be able to grab that part too. D is based on or depends. It depends on T. So if D depends on T, D is the dependent and T is the independent. That makes perfect sense. Yes? Now, here's the really not cool thing, but we need this equation to answer these last two because there's no information up here at the top about how fast it travels or where it starts, is there? I mean, it tells us that the rocket is 2.5 feet tall, but it doesn't tell us anything else in the wording, does it? Okay, so what's my rate of change, and how do you know?
Distance traveled in time.
I'm sorry?
The distance traveled in a matter of time.
Okay, it is the distance travel. Absolutely. It is the distance. And what is that distance in this particular case? 5. How did you know that? It's with the time. It's with it. And that's where our rate of change goes. All right? What's the initial value? 2. So in this particular case, it's really easy. The equation line was already given to us. D equals 5T plus 2. Now let's look at the actual situation. We said the rate of change is 5. What does that mean in this problem? Amanda? Very good. The rocket travels 5 meters per second. 5 meters per second. And then what's the context of the initial? Oh, go ahead, Ashley. Question?
How do we know that it's 5 meters per second?
How do we know it's 5 meters per second? Well, you agree that it's 5.
Yeah.
Okay? And what is the distance traveled in meters, so I know it's going to be 5 meters based on the time in seconds.
Yeah, but how do we know it's just 1 second?
What would the number, or what is slope? What is slope?
Rise over rise.
Thank you, rise over run. And what would 5 be in fraction form? 5 over 1. And that's how you know. That's a great question. And then, since we're talking about meters per or based on, remember how we talked about that per, the kitty, sometimes tells us that rate of change? Well, the first value that you're talking about goes with the top, and the per goes on the bottom. Okay, that's a great question.
I just didn't know if it would always just be 1
If it's a whole number, yes. But you're going to see another question coming up where the bottom number won't be a 1. Okay, so look at it again. Great. And then the initial value is 2, we've already said. What does that mean in this situation?
That is started at 2.
How in the world is a rocket going to start taking off at 2 feet or 2 meters high? Yeah.
Sitting on a stand.
Sitting on a stand, sitting on a platform. Do you understand how you can come up with or decipher that kind of information? Absolutely. It just didn't happen off the ground. It started on a stand 2 meters in the air. Okay, so the launch point was 2 meters above the ground. Now, you could include, probably on a platform if you wanted. But that's what we're looking for here, is to figure out all the things that are going on in a situation, even the ones that weren't said or stated. Questions on question number 1. So there we looked at it in a situation where we were given a equation. That was pretty easy. Let's look at the next one. Okay, now we're not given the equation, but we are given a graph. But we already know a lot of things about graphs, don't we? All right, so let's look at it. The cost for 6 people to travel in a taxi in New York City, based on the number of miles driven, is shown by the following graph. Somebody tell me my dependent variable. C, how do you know that? It's based on. How many people see that it's based on that? How many people looked at that and said, hey, definitely going to be C? Anybody look at the graph? One person. Okay. Then what's the independent variable? M. How do you know that? Still, it's right there in there. Now, I want to look at this exact same thing in a different way. In the last one, we were given the equation, and then I asked you to look at the sentence, right? Now you guys jumped right on the sentence, but now I want you to look at the equation. Where is the independent variable all the time in a graph? What? On the side? On the left, always? It's the y-axis. The independent variable or the input is on the y-axis.
Or no, that's the dependent variable. Wait, which one are we talking about?
Independent variable.
Independent variable.
Very good. Independent variable or the input is on the x. One more time with me. Hands together. Input, output, domain, range. Independent, dependent. X, Y. See how it all goes together, just those different names. So technically, we could have just looked right here and said, hey, the dependent variable is C. The independent variable is M. So there's 2 different ways we can find out that same information now given a graph. Okay? All right, so what's the rate of change? Who said that? Riker? How'd you get 1 over 2?
It goes up and 1 and over 2.
Man's a genius. We got to find some lattice points. Here's some lattice points. Everybody remembers what I mean when I say lattice points, right? Okay, we find some lattice points, and we just count your rise and your run. It runs 2, this is our bottom, and it rises 1. So absolutely, just like Riker said, our rate of change is 1 over 2. Back to Ashley. 1 what? 1 what over 2 what? Sorry, I'm looking for my eraser. I don't like the way I wrote that. 1 over 2. Rise over run. It rose 1 what? Dollar over 2. $1 for every 2 miles. Now you see how I'm bringing back what you asked in the last one. Okay, so our slope's not always going to be over 1. Okay, we'll come back to that when we get to the context. So what's my initial value? Nick,
2,
how do you know that?
because that's when the line crosses the y.
Absolutely. My initial value is 2, which is my y-intercept or my initial value. I just want to throw one more in here, just kind of seeing if you remember. What else? Nick just said, I can see that's my y-intercept. We've said that that's my initial value. I need one other way to know that this is my initial value. Yes? Very good. It's the value when your input is 0. And our y-intercept always has a x value or input of 0. Good. Thank you for remembering that one. That one's the one we usually miss. All right, so now that we have all that written down, what's my equation in my line? Ashley? C equals 1/2 m plus 2. Good. Now let's look at the context. What does the rate of change mean, Ashley? Good. We travel. Oh, look at this. I'm going to really mess with you. We travel 2 miles for every $1. Am I right there?
Yeah.
Anybody have a problem with that?
Switch your
I switched it around, didn't I? It means the same thing.
But if you switch the numbers around, what do you do?
I mean, I go 2 miles for every $1, I get it. But that's not rise over run, right? I want to say it another way. I get 2 miles for every $1, or, okay, for every $1, I go 2 miles. How about anybody else? Anybody else another way to say it? Yeah? Okay, I already got that one. How about this one? Good job. 50 cents per mile. How did I get 50 cents per mile?
division.
Just half $1, right? Now think. This is what we're talking about when we say contextualize, context. We just said that rate of change 3 different ways. We have to have a really good understanding of what the context is, okay, what the situation is. Because I might say to you, 2 miles for every $1, and say to him 50 cents per mile. Well, that's the same thing, but I said 2 totally different things. Sometimes we can't make that connection, right? That's what we're looking to be able to do. Context of the initial value. Zoe? What starts at $2? Cost, okay. So what's that mean? Yeah, that's the fee just to get into the taxi. That's what we're talking about, right? So it's $2 just to tell the taxi where to go or to use the taxi. All right. I will post that on your Google Classroom so you have it as a reminder. What's our homework?
It's evens.
Evens. What do you do after you do the evens?
Read and highlight.
Watch the videos. Check yourself. Y'all have a great day.